Hi and welcome to Calculus 30 with Miss Verity. Today we're going to be looking at 4.10 Implicit Differentiation. So each function that we have differentiated so far has been written in the form of y is equal to f of x. So functions written in this way are explicitly defined. So implicitly defined relations such as x squared plus y squared minus 2x plus 4y minus 20 equals 0 do not have the function expressed in terms of x and therefore don't have like a y is equal to something. So for our first example, determine the value of dy dx at the point 5, 1. So we've got x squared plus y squared minus 2x plus 4y minus 20 is equal to 0. So we are going to start and we are going to move the 20 to the other side. And I'm just going to rearrange. So x squared minus 2x plus y squared plus 4y is equal to 20. We are technically going to complete the square for each part. So we're going to end up with x minus 1 squared plus y plus 2 squared is equal to 20 plus 1 plus 4. I'm not going to go into how we do that. We're just going to trust me for now. So we want to get y by itself. So we've got y plus 2 squared is equal to, well, now we've got 25 minus x minus 1 squared. So I'm going to take the square root of both sides and end up with y plus 2 is equal to, well, in our brackets, I'm going to square this guy and simplify. So we'll end up with 24 minus x squared plus 2x because we would have got x squared minus 2x plus 1 and we'd have subtracted that. So simplified, it looks like that. And because we squared, we're going to get plus or minus. So now we've got y is equal to negative 2 plus or minus the square root of 24 minus x squared plus 2x. So we haven't even taken the derivative yet. So we would then take the derivative of that. We're gonna not do that. Follow my thoughts. So find dy dx for each. So dy dx is the derivative of y with respect to x. We can also call that y prime or f prime of x. It's just taking our derivative. We have to have y equal to 0, or we have to get our y by itself. So dy dx is equal to 4x plus 0. Technically, there's our derivative. On this side, we want to get y by itself, so I'm going to move y to the other side. X plus 4x squared minus 2 is equal to 2y. Divide everything by 2. 2x squared plus 1/2 x minus 1 is equal to y. I'm just going to put my y out front when I take my derivative, so 4x plus 1/2. There's our derivative. So we have to get y by itself to solve for dy dx. So we know that the derivative of x to the 10th with respect to x is 10x to the 9th. And the derivative of y with respect to y is 10y to the 9th. So we're just following our power rules there. But what is the derivative of y to the power of 10 with respect to x? So we can only take derivatives of y's with respect to x's when we've got our y isolated. So we're going to use our chain rule. So our first one, we're looking at the derivative of 8x cubed with respect to x. Well, the nice thing is when you've got the derivative of x with respect to x, that just kind of cancels out and you just use your power rule. So we've got 24x squared. Here we've got the derivative of 8y cubed with respect to x. Well, so kind of our derivative of our y. So d 8y cubed over, this is b with respect to y, times with our respect to x. So here, those would cancel out and we just take our derivative and we get 24y squared times dy dx. Our derivative of x with respect to x, so again, those are going to kind of cancel out. Derivative of 6x is 6. And our next part, so d of 6y with respect to y times the derivative of y with respect to x. That cancels out dy times or 6y times, not 6y. Derivative of 6y with respect to y is 6 times dy dx. This is a bit of the why behind it. I'm just showing you what the why is. We're not necessarily going to talk about using the chain rule. Basically what it comes down to is if you're taking the derivative of y with respect to x, you take the derivative of y times dy dx. That's basically what it is. So determine the value of dy dx. So here's that same equation we had before. We had to complete the square on two parts and solve. But if we can just use implicit differentiation instead, this is what we're going to end up with. So we're going to take the derivative of each piece. I'm just going to write my equation down below here. Okay, so my derivative. So my derivative of x squared is 2x plus my derivative of y squared is going to be 2y, technically to the power of 1, times dy dx, minus my derivative of 2x with respect to x is 2, and my derivative of 4y is 4 dy dx minus this would be 0 equals 0. So basically, when you take the derivative of y with respect to x, it's your derivative times dy dx. And then when we're using implicit differentiation, we basically now just want to get dy dx by itself. So 2y dy dx plus 4 dy dx equals, I'm going to move my non-dy dx's to the other side, negative 2x plus 2. So factor out my dy dx, and I'm left with 2y plus 4 equals negative 2x plus 2. And to get dy dx by itself, we're going to divide both sides by 2y plus 4. So dy dx equals negative 2x plus 2 all over 2y plus 4. We're then just going to simplify as much as we can. So everything can be divided by 2. So negative x plus 1 over y plus 2. And specifically, this question was asking us to find the derivative at the point 5,1. So we're just going to plug those points in. Technically, we could have also done that at this step, but we can do what we want. So negative 5 plus 1 over 1 plus 2 equals negative 4 over 3. There's our derivative. Okay, so comparing the two techniques, we see that implicit differentiation has several advantages. So to use explicit differentiation, you must solve for y, which can be very tedious. We saw we had to complete the square on both sides, and often actually impossible to do. You do not need to isolate y if you use implicit differentiation. So if you wish to differentiate explicitly and the process for solving for y, you must obtain more than one function, then you need to make a decision as to which explicit function contains the point, and then you'd have to find the slope, blah, 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 blah. Implicit differentiation yields only one expression which you can sub your x and y coordinates into. So notice when we did our big thing, we ended up with two different ones. So we'd have to figure out, okay, what point is 5 going to be in? So explicit differentiation is often more involved since solving for y is very involved and difficult. Okay, so for each function, find dy dx using implicit differentiation. So we're taking our derivative of each piece. So derivative of x squared is 2x minus 4y dy dx equals 0. So get dy dx by itself. 2x equals 4y dy dx. You could have also moved the negative 2x to the other side, or the 2x to the other side. It does not matter. Divide both sides by 4y. This reduces to be 1, and we get x over 2y is equal to dy dx. There's our derivative. Our next one, 2x plus this, notice, is 3x times y. So that is a product rule. So we've got our derivative of the first times our second plus the derivative of the second. Well, the derivative of y, this is y to the 1, would be 1y to the 0 dy dx. Well, anything to the power of 0 is 1. So it's just dy dx times the times the first minus 2y dy dx, and derivative of 9 is 0. Okay, perfect. So we want to get dy dx by itself. So we've got 3x dy dx minus 2y dy dx equals negative 2x minus 3y. We'd really want to watch if that was a negative, because we'd have to distribute the negative through, but it's a positive, so we're okay. Factor out dy dx, and we're left with 3x minus 2y equals negative 2x minus 3y. Divide both sides by 3x minus 2y. So you might be thinking to yourself, ooh, look, common terms. But they have to be, it has to be common to everything, or it has to be perfectly identical in order to reduce. We've got, if I wanted to take out the negative 1, you don't have to. We've got 2x plus 3y. And in our denominator, we've got 3x minus 2y. And those are two completely different things, so therefore we can't reduce. And that would be our derivative. You could have left it as that. That also works as your derivative. It's simplified. Okay, so for each function, find the slope of the tangent line at the point 2, 1, and then find the equation of the tangent line. So our first one, we've got, let's just start taking the derivative. So 4x minus, we've got a product rule right there. So our product rule is 8x times y. So I'm going to do subtract derivative of the first times the second plus derivative of the second times the first minus 3 dy dx plus 0 equals 0. 4x, I'm going to distribute my negative just to make sure I'm not going to lose those, because eventually that's going to screw us up if we lose negatives. All right, so get dy dx by itself, negative. Honestly, if we're working on skipping steps and being efficient mathematicians, we might already start taking out our dy dx, and we're going to be left with negative 8x minus 3, and on our other side, we're going to have negative 4x plus 8y. Divide both sides by negative 8x minus 3. That reduces to be 1. And we've got negative 4x plus 8y all over negative 8x minus 3. There's nothing common to every single term, so therefore we can't reduce. That's our final answer. And let's do B. So first of all, you want to ask yourself, do you like the look? Personally, I don't. I would switch it to be xy to the negative 2 plus 3y equals x squared plus 1. So now taking our derivative, we've got a product rule. So 1 times, so derivative of the first times the second plus derivative of the second times the first plus 3 dy dx equals 2x plus 0. So I'm just going to simplify y to the negative 2 minus 2y to the negative 3x dy dx plus 3 dy dx equals 2x. Taking out my common factor of dy dx, I'm left with negative 2y to the negative 3x plus 3 equals 2x minus y to the negative 2. Divide everything by negative 2y to the negative 3x plus 3. Reduces to be 1, and I'm going to run out of room. dy dx equals 2x minus y to the negative 2 all over negative 2y to the negative 3x plus 3. Again, there's nothing common to every single term, so there's our derivative. And then I say because we haven't actually answered the question. We want to find the slope of the tangent line at 2, 1. So I'm just going to bring this back up. So we're doing it at 2, 1. So 2 times 2 minus 1 to the negative 2 all over negative 2 times 1 to the negative 3 times 2 plus 3. Remember, negative exponents just mean it's the reciprocal, but the reciprocal of 1 is 1. So 4 minus 1 over negative 2 times 2 is negative 4 plus 3. We get 4 over negative 1, which is negative 4. So that's our slope. We already know our point, so I would do slope point form. Y minus 1 equals negative 4x minus 2. There's our equation of the line. I'm not going to do example C. It's literally the same thing.